So when you think of railway air conditioning, what comes to your mind? Let's say you were the person designing an air conditioner for a rail coach application. That's for comfort. So what comes to your mind? What are the things that immediately come up? What would be a typical constraint that you would be aware of? Yeah. Perfect, very good. So we need to be present to Mumbai weather and Rajasthan weather at the same time. What else? So as you speak, we will put down some of these things, as if we were designing it together, because that will get a flavor of the case study and how we designed the product come up. So first thing we said was variation in ambient. Yeah. Okay. Okay, so for the time being we can remove this, and we will use it later on. Okay, so this arrangement, if some of you are wondering why I made this arrangement, is in the course of this product design, there was a consultancy project, and that resulted in a paper that was published in one of the engineering journals. So I have the originals from that time, and I thought I will share that with you. So the idea was to have it not reflect. So we're going to use it later on. So coming back, so design considerations, let's say this, design considerations. So So the second was, someone said size. Size is very critical, because we're going to use the size for the passengers, or we can use it for equipment. So should we say size and weight both? What else? All right. So when you say noise, meaning the noise in the occupied space should be minimal, right? And so for some of you just getting connected, we are looking at what are the design requirements for a roof mounted package unit for railways. So we are going to look at a case study today. This is a product that I designed some time back, and it is today a running product for Indian Railways, and I want to give you some more idea on that. But right now let's try and connect with the first lecture. When we are mapping requirements, what are the things we look for? So, and this is something which will also help you do your assignment, because you're going to look at requirements in a different context. So be involved and participate, and that's going to make it easier for you to do the assignment and also connect to the design process. So we have some good inputs coming in. What else?
Power requirements.
Yeah. So when you look at power requirement, you're looking at single phase or three phase, what voltage, what frequency. And then in railways, it is a little more complex than just that. We look at end-on generation, which is a generator car on the train from where 750 volt is transmitted across the train, and then there are transformers in every unit. So that's another complexity that we have in a moving train. And then we have some coaches which have self-generating type of coaches. So there are batteries, and there's an alternator, and the alternator is powered by the movement of the coach. So it is connected to the wheels, and there is an arrangement. So that power is not identical to the power available from end-on generation type of generators because of the waveform. And again, we will look at how that has an impact on reliability and performance. So what else?
Efficiency.
Yeah. Yeah. So when you say controls, I'll broaden it to say controls and safety. So controls includes setting the temperature. So you often noticed at night people want the temperature to be raised. So if you've traveled by an AC coach, you would have seen this constant tussle between different passengers, some wanting it a little cold, hot, so the attendant needs to be able to vary that temperature. Also an ability to switch from heating to cooling. So someone talked about the ambient. So the ambient changing, and we would need the ability to heat as well. So this would mean control of mode. What else?
Life cycle.
I didn't hear you properly.
Life cycle.
Okay. So this impacts the material use, the kind of robustness that we have. So can we think of something more? So I'll help you with some other things that I got to know from experience. So one of the ways to check the suitability of an air conditioner is how soon can we pull down the temperature in a coach. We need to have it ready for passengers to board the train, and many times it's standing in the sun. So the ability to pull down the temperature would be one of the requirements. So we were on 7, let's say this is 8. So when we look at pull down time, it has to do with the size of and by size I mean the capacity of AC unit. Then we can also look at the maximum load in the worst ambient. It would be one of the critical things in Rajasthan when the
Exactly. Pull down time would also depend upon the environment.
Yes.
We are running the train.
Right. Right.
We're not only going to cool the surroundings, we might actually have to heat it as well in case.
Right. Right. So we can all right. So from a pure analytical perspective, you're absolutely right. But what happens is in this, the critical condition ends up being pulled down in hot weather. Because the moment you have occupants inside an insulated compartment, so it is double glazed glass windows, then you have insulation on the walls, the roof is insulated. So heating does not end up being a critical thing. Otherwise you would say what is the time required for raising the temperature. But for sure we need to be aware of what capacity of heaters we are going to include. But in the case study, we did not find this to be a constraint. But when you are looking at it from a requirement definition, you are absolutely on the point.
Saying that if we do not cool the surroundings, automatically we heat it.
No, it's more like in winters, if you have a fairly large number of persons in the same room which is insulated, then even without a heater, you very soon begin to feel comfortable because the lights, the load of the occupants begins to raise the temperature. Right. But if you look at a summer condition, then we have a combination. The entire coach has been heated because there was no air conditioning, so there's been conduction, and then people are entering. So that is another heat load. So overall, the whole thing is aggressive in terms of what is needed, whereas the occupant heat load is enabling for getting the temperature to the comfort point when it is a heating application. So that is the main difference. But in a requirement definition, yeah, so let's put it as a heater capacity, right? Because your question may become very relevant if you were looking at it in a climate like US, where the ambient is in sub-zero conditions, -7 and all that, and how soon can we get the temperature up? So then that could become the dominating requirement in another country. So we also would like to define what cooling we need at what condition, right? So performance at defined conditions. So in railways, there is an organization RDSO, and they were already having data based on a different kind of technology. That was the underslung technology. So these conditions were pretty much well defined in terms of indoor conditions. So the indoor conditions, 25 degrees C dBT, 16 degrees C WBT. This was the test condition at which we had to look at capacity. And in every coach, there are 2 units, 2 roof mounted package units. But then again in the requirement definition stage, we will also need to say how many units and what level of redundancy. So number of units and circuits, and I will explain a little more on the circuits. So on the performance side, we have indoor conditions and we have outdoor conditions. So the outdoor conditions were progressively redefined. So it was 46 degrees centigrade in the beginning, and then it was raised to 50. Now this is another example of deriving a condition based on real applications and a mismatch between the test condition and a real condition. So to appreciate this point, I will switch to a slide and give you a little more perspective on the type of assignment this was. The case study originated out of Railway's intent to switch from a particular type of air conditioner to a roof mounted air conditioner. So Railway air conditioners until 1992 used a technology which was under-slung condensing units connected to an evaporator which was mounted above the entry area. So under-slung split systems with a single semi-hermetic compressor, and they used R12 as refrigerant. We are going to come back to the requirement definition, but what I am going to share with you now will put another perspective of how the requirements were flowing from an earlier design to a new design. So this is a view of a train, and if you look at the area, so this is the area where the condensing unit is there, and this part is not so clear. So the next slide we can see it a little more clear. So there are 2 fans, the axial flow fans, and then there is a semi-hermetic compressor which is driven by an electric motor. So this is a very bulky equipment which was using R12 as refrigerant. It was imported, and then a part of it was indigenized. Stone India was the company that was the only supplier for these equipments. So Railways was in having a need to put in a large number of air conditioned coaches at the time this project was envisaged. And the intention was to go in for something which is locally developed. At the same time, it is easy to install and it is relatively more affordable, so that a large number of air conditioned coaches can be introduced in Indian Railways. So that was more or less the background, and it was also the time when I joined Feders Lloyd as manager for R&D. So my predecessor had already done some prototyping work based on RDSO project which was given to Feders Lloyd and one other company to make a prototype and test out the concept of a roof mounted package unit. So what does the roof mounted package unit lead to? It leads to a unit of this type. So if you look at these 2 units, these are on the roof of a train, and they are connected via ducts to the occupied space. So every coach would have 2 units on either side, and this is for the standard application. If there are smaller coaches or first AC coaches, they could have 1 unit or different capacities. But the time when I was involved in the project, in the case study I am referring to, it was 2 units to 1 coach. So now we switch back to the requirement definition, and this was to give you a glimpse into what was. So to have it on the roof, this was another and this kind of answers the earlier question about size as well. And what else beyond that? Quick installation and service. So earlier the unit would require 4 days to install in a coach. This would be installed in 4 hours. So that was the kind of design intent that was there.
Load on the system?
Sorry?
Load on the system?
I didn't get the question.
Capacity of the system.
Okay, so 7 tons at these conditions. This is how it was originally. Some more requirements that you can think of. you begin to think, and I am happy about that. So, you are getting engaged. So, when you draw up a requirement for a new product design, this is the thing you will do. You will have something very explicitly stated by the customer, and here it was that it has to be on the roof, it has to be quick to install. There was a certain capacity requirement given, and then there were certain things which were not really known. So, at the time I was involved in the project, I did not know all the parameters. I knew what was on paper. So, there was a requirement from the customer which was on the size, which came in like this. So, this was 2100 millimeters. This was directly related to the width of the coach and the required interface for mounting it. And then the rest of it was all for us to design except the ducts. So, there was a duct here for return air to come in, another duct here for return air to come in, and a supply air duct on top. And then there was a requirement here which was 445 millimeters, and then there was a curve. So, the max limit was 620, and this was to take care of the coach clearing any hurdles on the way. So, this is the max height limit, and this is to do with the space constraints. Then we had to look at interfaces on how to mount it. So, if you look at this area, a typical mount would include a projection on the side, which was again defined by the customer as 75 millimeters here and another 75. And then it is not defined that there needs to be a vibration isolation at what level, but the vibration conditions were defined. So, in railways there is something called shunting shocks when coaches are being assembled together, joined together. So, there will be a shock. So, we need to define the level of shock. So, in the longitudinal direction, the shock is defined as 3G, shunting shock, so instantaneous momentary shock, and then vertically 0.5G, and then there will be a transverse number which was 1.0. So, these were the kind of conditions. So, you can relate to it that while the coach is in movement, there will be some movement perpendicular to the track, some up and down because of the joints, and then I talked about shunting shocks. Now, how do all these things matter? In our component selection and in a design of piping, we need to be aware of all these things to be able to withstand the full life of a AC unit. Now, with all these things given, we began by looking at design of the unit. First of all, component selection. So, we have gone through a lot of component selection exercises earlier. I have shared with you different compressors, all that. So, here the 7-ton requirement was split into 2 compressors with 2 independent refrigeration circuits. So, each compressor was having a capacity of 4.3 tons, and this came out from what was standard available. So, there was something available at 45,000 BTU and then 52,000 BTU per hour and all that. So, we selected a 52,000 BTU per hour compressor as a baseline based on the railway requirement and the evaporating and condensing temperatures of this compressor. Right. So, what are those conditions? At 2516, we opted to look at 5 degrees centigrade evaporating temperature. Do you remember some of these parameters from the thermodynamics that we discussed? Can you relate to evaporating temperature for a compressor? If you can't, we can talk about it also. If you can, nice. So, the intent was that at these conditions we should be able to get 3.5 tons from this compressor. So, these are off design conditions, they are not the rated condition. This 4.3 ton is the rating condition. Now, having selected a compressor, we also need to look at selecting the cooling coil, and here there was a big challenge for me because in the organization there was not any heat transfer software that was available. I had not done anything during my stay in IIT on designing a heat exchanger. So what was available to me was existing product designs and some way to scale them up or down based on an application. So the closest reference I had was a 3-ton unit, and based on applying scaling and the need to circuit balance, we made a coil design which looked like this. It was a 4-row coil, staggered, and the total height was equal to 19 tubes, 3 by 8 inch diameter. And then the next question was how many circuits. So how do you look at the number of circuits in this whole design? So if you put this as 1 row, this is the 2nd row, this is the 3rd row, and this is the 4th row. Or before doing this, let me also share with you one of the schematics of this unit as to what the layout looked like. So now is it okay? So this is the evaporator coil that I am talking about. There are 2 of them, and then this was the overall layout. So from the dimensional requirements, we tried to fit everything within the available space. So there is a compressor here which is exposed to the ambient. There is a condenser coil which is vertical. The second condenser coil which is vertical, there are 2 axial flow fans, propeller fans in the condenser, and then there is 1 blower motor connected to 2 blowers, and then each of the blower is drawing air over the coil here and here. So the circuit that I was sharing with you was for these 2 coils. So we came to the dimensions based on scaling of equivalent configurations. Then we also had reference of what was working already in railways. So based on that, we made some calculations to ensure that there is no condensate carryover. And if you refer my notes, 2.5 to 3 is an acceptable phase velocity for no condensate carryover. So keeping that in mind, we had the airflow selection done, and the circuit by circuit balance was one of the challenging things as to how do we have the same circuit load per circuit. We did this through trial. So we did experiments to see which circuit was being fed refrigerant which was a little higher than required, and which was being fed a little lower than required, and that requires a certain understanding of some other components of a refrigeration circuit. So let us say we have air coming in at 25 degrees centigrade, 16 degrees centigrade, this is dry bulb, this is wet bulb, and then we have different tubes in each of these circuits. So if you look at the temperature difference for all the tubes in this section, they would encounter the highest temperature difference if we were having refrigerant entering at 5 degrees centigrade, and this side would have the lowest temperature difference. So one way of balancing is that midway in the coil we swap. So we have a tube which connects this to this, and we connect this through another loop to this tube. So we kind of manage balancing the circuit, and this we could do it even before doing our first trials. So we could envisage that there is going to be a difference, and then the 2 inside circuits, again midway in the coil design we swapped them, and then there were 4 outlets available from each of these circuits. So we put a side glass in each of these circuits. So a side glass essentially allows for refrigerant to enter that device, then there is a glass opening and there is an indicator for moisture. So the indicator which is in the center changes color based on whether there is moisture or not, and that is a separate requirement for a refrigeration system. And the other part is you can see whether you are getting 100% vapor or a mixture of vapor and liquid. This setup enabled us to look at which circuit was overfed with refrigerant and which circuit was starved of refrigerant when we were doing the circuit balancing. So the feed to each of these circuits was again through a capillary, and it was possible to resize the capillary, which is the expansion device, so that finally, there is a balanced load, and this was a purely experimental approach to getting to a balanced circuit. So, this is one part of the design, and it also illustrates that when we do not have the best analytical software, we can still achieve the objective of a design by looking at some very fundamental and direct ways of measuring the performance of a subsystem. A subsystem here being the evaporator coil. The next risk in a system is of low load leading to some refrigerant in liquid form getting to the compressor. So, what we did was we put in an accumulator, and I have not discussed with any of you an accumulator before, right. It is just a device which will take care of all liquid getting entrapped and only vapor going to the compressor. So, this circuit actually gets into a header, and the header is feeding the accumulator, and inside the accumulator there is a tube which goes to the compressor suction. Now, this tube has a small opening at the bottom, allowing for oil to be picked up, so that it continues to be in the system. I had fun actually designing this product, because it was my first real product, and I had given up what others considered as very good companies. So, I worked for ICI, Imperial Chemical Industries. Before that, I worked for Procter & Gamble, and each of these companies gave me good perks, but no real content to create a new product. When I was here, I was actually driving everything. All the decisions for this product were my domain, no interference, except one occasion where the chairman came up and said, you know, why not doing what the competitor is doing. That was the only one instance where I found that there was some authority trying to dictate what I should be doing, and I could handle it on the shop floor in front of 10 other people. I said, look, there are two ways of doing this. Either you tell me what component I will use, and then you are responsible for the result, or you let me choose the components, and then I will be responsible for the result. And fortunately, that guy was very mature. He was like 70 that time. He understood, he backed off, and post that. So, I had my freedom. So, I had all the fun, all the experimental freedom to choose components, try them out, but ultimately responsible for delivering the product. And the product delivery means railways will come in. So, they will have a set of senior persons along with some technicians. They will test the product. They will do their own bit of verification on specs. They will count the number of fins that we said we will put in the evaporator coil, the number of circuits, what source of components we are using, what compressor we are using, and all that. And that is the fun part. But before we could reach there, we had to make sure that the product is really worth presenting to the railway officials and it meets the spec. And these are some of the things that we did, which were which you would not find in textbooks, which were making use of what I learned here, but it was also applying something using what some of the component suppliers were sharing as information and some of my own innovation. So, where were we? We were on designing the evaporator coil. So, the basis of design was scaling up a 3-ton coil. So, that was simple. Then balancing the circuits. So, we know that there is a temperature difference which is very different here than it is over here and somewhere in between. So, we apply a very fundamentally simple rule that we are going to have the same number of tubes on one side and then the other side and expect that to balance out, and then whatever remains we will change the length. So, we use capillaries, and if I remember right, these were 0.055 inch capillaries, and there were two different lengths. So, for the outer circuits, the two outer circuits, we could use 35 inches, and the inner circuits had to be, oh no, it was the other way around. So, these were 29 inches more refrigerant flow, and these were 35 inches in the center. And this was done so that finally we see clear side glasses at the outlet of each circuit. Now, having done the evaporator, then the condenser was relatively more simple. We made use of a 3-row condenser coil, again staggered 3/8 inch diameter. So, for those of you who want to take some notes, there is a 3/8 inch outer diameter, 1 inch vertical pitch, and the distance between this applies actually to both the evaporator and the condenser. So, this distance was 22 millimeters row to row, and this was 1 inch or 25.4 in both the types of coils. So, here we had discharge gas coming in on top. So, we make a header which feeds in these two and the central circuit, and we apply the same principle. So, in a condenser what is going to happen when you are doing testing, we are going to have hot air come in at 50 degrees centigrade and leave it somewhere like 57 degrees centigrade. Again we need to balance the circuits, and here there was not any capillary available to adjust the flow. So, it was what it was, and there was a certain inefficiency which we knew would happen, but 3 circuits made this whole thing a little simpler. So, one circuit we would just get it right down into a header here, and these we would swap midway. So, this tube would connect here and this tube would connect to the other side, and again we would put in a side glass with a moisture indicator right at the bottom of this coil to be sure that when we are charging refrigerant, we are having liquid, subcooled liquid at the outlet of the condenser. So, with this done and the capillary selection was arrived at by some experimental means, we had a product ready for testing. So, the other components that we had to select were fans and motors. So, the fans for evaporator, we had a centrifugal blower, and as I shared with you, there were 2 blowers on 2 sides of a motor. So, with air coming in and leaving, here again air coming in and leaving, and this was fed into a common supply air duct which was connected to the coach central duct. So, for the condenser, let me also define for you. So, the blower motor was 1 HP, 1440 RPM, and here in the condenser we had 24-inch propeller fans. So, some of this heat exchanger design was also simple based on experimental data that is available for other package units. So, let us say a 7.5 ton package unit is available with testing done at 35 degrees centigrade. So, it is possible to upsize or downsize that coil and get a data point. So, the condenser we have and 2 motors. These were 0.75 HP and 930 RPM. So, again all of them were 415 volt 50 hertz rated condition, both for the blower and for the condenser. So, we made a selection on the compressor, we made a selection on the evaporator, fan, condenser and blower. On the condenser, if you want a little more detail, it was length between tube sheets was 1320, the height was 22 tubes, effectively 22 inches, and they were vertically. So, the condenser, if we were to look at, would be a configuration where there would be a fan over here and another condenser on this side, and this would be the base. So, ambient air comes in from both sides, and if you look at it longitudinally, there would be another fan at the back like this, and then this would be fed in towards this, and mounting was a flange mounting. A lot of this engineering detail I am not in a position to share, because whatever company I worked for, it is their proprietary and all that, but whatever was used in some research papers, I am going to share with that in a vibration study that we did, right. So, then this was we came to a point where we had a prototype which could be tested, and then there are certain things that were to be considered after the prototype was made. So, things like how do you drain condensate? So, this becomes more complex in a railway application, because you have water and the water is going to splash because of movement, and then there is going to be static. So, you have a powerful motor drawing air over a coil which is 4 row thick, then there is a filter, and all that put together means a static. The static of 20 millimeters will tend to hold condensate between the blower and the evaporator coil. So this was what we started with. We had a coil like this with some padding at the bottom, and I'm showing one side of the coil. So this is going here, and we have the blower. So because it's static over here, there would be an accumulation. So if you looked at water, it would be higher on this side and relatively low on this side. And then if we try to drain this water to the outside where the static is atmospheric, there will be a build-up. So this is something we never got from railways as a requirement. We did not know it until we put the unit on a train and it went a couple of times to Bombay, and then we got passengers complaining that there is water being thrown in. Our first guess was that Bombay is humid, there is rain, and therefore it is rainwater from the trough. So we went, and it was rainy, and we found that there was water from the trough which could also spill in, and that was another thing that railways had to take care of. But then we also found that this was a concern area. So the design had to undergo some changes. So the changes were to put some kind of a redesigned drain pan, so that if there's any splashing, the water will not go out but it will fall back in. And then the drain was to go out into a cup, a siphon kind of an arrangement, so that the static was effectively addressed. Again, this is not something you would find in books. You need to find an innovative way to solve the problem when it occurs. It's totally unknown at the time we were making this design. And this effectively solved it. So we created a head of 25 millimeters, and then there was no problem for water, and we put the drain on this side. So the water could actually come in and get drained without any issue. But it took some trips to a real working unit, finding out and also addressing other things. So other than this part, there is a slope that is required between this and the connecting part. So before we made this arrangement, the condensate from the drain pan, so if you make another drain pan, was directly connected to the coach and was expected to go down. There was a height difference between this and the drain pan. So instead of water flowing like this, they had created a condition where it was in any case designed to accumulate. So you have static, and then you also have a difference in level. But all these were related to solving problems that essentially did not address some things which were system level things, and certain other things which had to do with the interface. So in this design, we can look at some other unique things that were needed for a AC design for mobile application. So you see a flexible connector. So this connector has a bellow which is made of copper, which is this part, and then there is a braid which is again made of wire, copper wire, and this is to impart strength, and then there are two connectors. The intention of using this between the compressor and the rest of the system was to allow for flexibility, so that because of train vibration and the heavy mass of the compressor, there is no fatigue on the tubing. However, when we put this unit in service between Delhi and Bombay, there were no issues. We were very happy, and we got repeat orders from the customer. So 4 units went straight up to 8. It was still like a pilot phase, so prototype to 4 units to 8 units, and those 8 units were put in service from Kapurthala ke baad kya? Amritsar. So Amritsar to Delhi. And within the first few trips, we got complaints that the units are leaking. And the first doubt normally goes to something to do with workmanship. So there were technicians, there was a whole team, so they were repaired, and they would go in service again and return back with the same complaint. The failure was exactly at the same point. So we had a major loss of credibility of what is happening with the design. And if there is a repeat failure exactly at the same point, then it is clearly not a workmanship or a manufacturing issue, it is a design issue. So someone who was very happy about having designed a product that works was suddenly under scrutiny. Bhupinder, what have you done? So the credibility was a major question mark, and everyone had ideas onto how the piping design should have been done. So I had a major difficult period for that 1 week, handling railways, handling internal customers and the company management as to what had gone wrong in the product. And I realized that I did not have all the answers. So the first thing that I had to accept was that I did not have all the answers. I did not have a clue as to why this was failing. And also, I had deliberately stayed away from vibration because I found it too complex a subject. I mentioned this in one of my earlier lectures. I said कि vibration कौन करेगा? You know, बाकी electives हैं सब कर लेंगे, but vibration तो नहीं करना. It requires too much of mathematics. So here I'm in field, having done a product design, and I'm hit by failures because of vibration. So the next best thing was कि अभी क्या हुआ? You know, I was still a few years out of college, so I said let's sign a consultancy project. So the moment I got management to agree on a consultancy project between IIT Delhi and Feders Lloyd, everyone who was advising me was suddenly shut. Because now whatever they say was subject to scrutiny. So if someone was wanting to advise to use 2 packless vibration isolators, type of tubes like this, to better take care of vibrations, but no one was saying that. Again, I got the freedom to do what I wanted to do, which means do a systematic study as to what is the root cause, at a tremendous cost. So for 6 months, we had no orders from the customer. But then there was no other way. Unless we get to the source of the issue, the design issue, there is no point going forward. So we did that, and that was what led to this research paper, which I will take in the next lecture.